Hello, folks. Welcome back to my stream. In preparation of Dub Dub, we will be first going through a couple of meetings, which I will be streaming live since those are public meetings and anyone can join in with a URL, which they publicly give on the calendars that they publish. So I don't think so. There should be a privacy-based issue. But first, let me go through some of the emails here. This is a bug in the VLLM project. This is a feature supporting multi-turn conversation for OpenAI Response API. Pip install kernels and fast path warnings. Migrate MOE kernels to torch stable ABI. Cohere to MOE model object. Pickstar process her image token properties. Support attention implementation SDPA dispatch. Explicit cache breakpoints and cache usage accounting in OpenAI compatible API. Reduce multimodal processing, cache contention, pump actions, stop, origin KV, transfer car classes for mixed full attention, update hub metadata, and model on a V2, KV cache multi-tier offloading a single batch lookup, support heterogeneous TP disaggregated inference, dependent on AIs to clusters, Falcon Mamba kernel for backboning, Wayland friendly interactive reset for report, exit report, cache positioning, some imports. Helium kernel dynamic token routing standards of Prometheus, human CP5 patch, asyncs at fault, AI bugs, SM90 FP8 mega MOE kernel split. This is cool. 62% cheaper. Since completionist group, I completed the whole Sanchez objective. Uh, it looks like I will have to complete it again.
A new era of creativity is here. Introducing the ProArt P16 and P14, powered by the all-new NVIDIA RTX Spark to create the ultimate agentic AI platform. Let's take a look. Stunning new look. Alongside the Nano Black, we're debuting a striking new Neo White finish. The new NVIDIA RTX Spark combines NVIDIA Grace CPU and NVIDIA Blackwell RTX GPU with up to 128GB unified memory. This revolutionary architecture effortlessly runs all your software to drive advanced agentic AI, while Windows on ARM ensures lightning-fast app loading. Thanks to its power-efficient ARM design, you also get all-day battery life, total creative freedom, anytime, anywhere. And to bring your vision to life, visuals look breathtaking on our top-tier Asus Lumina Pro OLED display. The ProArt P16 and P14 usher in a new era of AI-powered creation. Find all the details on the Asus product page, go check it out, and start creating without limits. A new era of creativity.
Okay.
When was co-host? Wait a second. I made a co-host the wrong guy, maybe.
That's fine.
Oh, sorry for that. It's probably because it's moving, so while you're
Yeah.
clicking, make a co-host. Okay, sorry, Venvo, now you're a co-host as well.
No problem, no
That's
problem.
fine. Okay. People are joining, that's great. Let's maybe wait for a few more seconds and then we can start. In the meanwhile, just a reminder to everyone else. So first of all, welcome to the reading group. And we usually record only the talk, which means I will briefly introduce the speaker. And afterwards, I would like to ask everyone to stay muted with the camera off during the talk. And if you have a question, do put it on the chat so that the speaker can also read the question afterwards and reflect on it, and you don't forget the question. But during the talk, we do not ask questions. And when I stop the recording, I will open the floor for questions so everyone can ask questions. I hope this is fine with everyone. I see that people are joining. I would like to ask Dong and Venvo, could you please help me to admit people? Because sometimes talking and pressing different
Sure.
buttons is a little bit difficult. Okay, great. In the meanwhile, let me introduce Maria. I am super happy that she accepted the invitation. I actually met her at a conference and I really liked her topics that she is working on. And what I could find online, she's a postdoc at Mathematical and Scientific Machine Learning at LMU Munich in Germany. I couldn't unfortunately find what you did before You came to LMU. So I remember we talked about something in France and something in Berlin, right?
Well,
So
France was a long time ago. That was still my master's. I was in Berlin for 1 year, and then I did my PhD in Munich as well.
okay. So I only remember that you made a tour across Europe actually when we talked. Also, Maria got an Eminota grant, and she will start a group very soon at U Darmstadt. So congratulations, Maria. We are really looking forward to your talk. And I suggest you start once I start the recording. Give me a few seconds to do so.
Recording in progress.
Hello, everyone. So first of all, thanks a lot for organizing this seminar and for inviting me. I'm, of course, really happy to speak here. So my talk is called How Long Does Infinite Width Last? And it's going to be about signal propagation in long-range linear recurrent models. So first, let me try to explain why people are now interested in such linear recurrent models from the point of view of how long-range sequence modeling developed over the last years. So by long-range sequence models here, I just mean machine learning or deep learning models that work on sequential data. So we have the inputs of the form x1, x2, all the way to xt. And we want to model long-range dependencies in these sequences. Okay, so we have a picture like this. All the way, let's say, in the 90s, people, or like the most popular models for sequential data were recurrent models, or recurrent neural networks, RNNs. And there are also famous RNN variants specifically for long-range sequences, such as the LSTM model. The basic structure of these models is that they keep the memory or the information about the previous inputs in the sequence by storing a hidden state vector, ht, and updating it over time. So we receive a new input and we update the hidden state at every time step. And because of this structure of recurrent models, the computational cost of such models is, roughly speaking, linear in the sequence length t. But the well-known problem with recurrent models is that they're prone to vanishing and exploding signals, which makes it hard to stabilize these models and train them over long-range tasks. And I will speak about this problem today quite a lot. But as you probably know, more recently, transformers have become perhaps the most popular architecture for sequential data. And in comparison with recurrent models, transformers need to store the representations of all the previous inputs in order to compute the attention matrix. And this makes the computational cost of transformers quadratic in the input sequence length t. So even though transformers perform really well in practice, the computational cost becomes really large on long-range tasks. And that's exactly why in the last years, people started to be interested once again in recurrent models for long-range sequences. And we have seen models like Mamba, which are recurrent models competitive on long-range data. So these modern recurrent models, they also rely on storing a hidden state, HT. And importantly, they use linear updates of the recurrent state for even more computational efficiency and for parallelism. So these models are exactly the linear recurrent models I want to speak about. They inherit the computational efficiency from classical recurrent models, but they also inherit the challenges with stability. So this recent interest in such models is specifically the motivation for a lot of questions I'm speaking about in this talk. Okay, so recurrent models are, you can see a basic structure of such models in the slide. They get an input xt at every time step t, and they update a hidden state that I will always denote ht based on the previous hidden state and the current input, right? And the important thing in recurrent models is that at every step, we use the same function to update the hidden state. And vanishing and exploding signals problem can happen in different components of recurrent models. For example, we say that the hidden states vanish if the norm of the hidden state tends to 0 as the sequence length or time t increases. Or we can say that hidden states explode if the norm of the hidden state grows to infinity with time. In this case, we have numerical instability. We cannot compute even the forward pass of the model, and we have a big problem, of course. The same instability may also happen in the model's gradients. They can explode or vanish, and then we cannot compute the backpropagation and cannot train a model, right? And another type of similar instability that may happen in sequence models is that the current hidden state forgets the past inputs. So it means that the dependence on the current state on inputs far in the past vanishes. Okay, and so in the literature, people have for a very long time recognized that this vanishing and exploding signals is a big problem in recurrent models. To illustrate this, here are two examples of papers. The first one is the famous LSTM paper from all the way back in 1997. So this paper is basically as old as me. And the second example is a very recent paper that introduced the linear recurrent unit model. So it's just, it's a very modern paper. But somehow both of these papers identify the vanishing and exploding signals as the problem that they want to solve with the methods they develop. And in classical recurrent models, such as in this LSTM paper, people try to ensure stability by architecture design. But in modern recurrent models, it seems like the focus is more on careful initialization and parameterization for stability. So over the last more than 20 years, people somehow developed a lot of different methods to ensure stability because they recognize that instability is a big problem in recurrent models. But now I want to ask a very simple question. Even before solving the instability, do we really understand when and why exploding or vanishing signals happen in recurrent networks? And of course, if I thought the answer is yes, then probably I wouldn't give this talk. So I will try to argue that our current theory is not very well suited to answer this question, actually. Okay, so now to illustrate the problem, I want to compare signal propagation in recurrent models and in feedforward models. In the last, let's say, 10 years, most of the signal propagation theory was developed in the so-called infinite width limit of neural networks. Here, the width of the network, meaning the number of neurons in the layer, tends to infinity. And now I want to compare how recurrent and feedforward networks behave in this limit, okay? So on the left-hand side, we have our linear recurrent network. It's the same structure than the previous slide. The only difference is that now the updates are explicitly linear, and at every step, they are parameterized by the same weight matrix W. And on the right-hand side, we have a network of exactly the same structure, but instead of using the same matrix everywhere, we use different independent matrices across time steps. So to distinguish the feedforward model from the recurrent model, I put the tilde above the hidden state here. And one note, here I define the models with complex weights because in linear models, it's somehow common to use complex weight matrices, but I will also often speak about recurrent and real and complex models separately throughout the talk. Okay, so what I want to tell you about these two models. Turns out, maybe surprisingly, that at infinite width limit, the signal propagation in these models basically behaves the same. The theorem on the slide says that suppose we initialize both models with centered Gaussians of variance inverse proportional to the network's width, then in the limit, the norm of the hidden state divided by the width n in the recurrent model and in the feedforward model differs by this only by this small O of 1, which just vanishes in the infinite width limit. Okay, so we see that, at least from the point of view of the standard infinite width theory that you would see throughout the current literature on singular propagation, recurrent models are not more unstable than the feed-forward ones. So from this point of reasoning, one can say that, okay, if we can stabilize feed-forward networks, we can also stabilize recurrent networks in exactly the same way. But in practice, we of course know that this is not true, right? People, I showed you, for 20 years knew that in recurrences, instability is a much bigger problem. And so this apparent contradiction is kind of what led me to study the questions that I present here. Okay, so in feed-forward networks, it's well known that we can ensure stability using the famous Glarot initialization. I define it here. So Glarot initialization for a matrix W is just a Gaussian initialization with variance of 1 divided by n. For real matrices, we just take a normal Gaussian, and for complex Glarot initialization, we will consider centered proper Gaussians, which means that the real part and the complex part are independent and identical, and the total variance of the Gaussian is still 1 divided by n. And so let's see in what sense this Glarot initialization is stable for feed-forward networks. So since in feed-forward networks, the matrix Wt at every time step t is independent from everything that the hidden state seen before, it's very easy to figure out how the signal propagation, or at least the norms of the hidden states, behave in such feed-forward models. Basically, for any initialization that is Gaussian with the variance sigma squared divided by the width n, we can immediately write a recurrence where the norm of the new hidden state is equal to the norm of the previous hidden state multiplied by our sigma squared, and edit the norm of the new input. And unrolling this recurrence, we get this expression where the dependence of the norm of the hidden state on the input k steps back is multiplied by this term sigma to the power of 2k, right? So now, from this form, we immediately see how it behaves depending on the different sigma values, right? So there's 3 possible cases here. The first one, where sigma w square is larger than 1, means that the impact of all the past inputs explodes with larger k, and the norm of the complete hidden state also explodes, right? So that's not a good case. Then second case, where sigma square is smaller than 1, means that the input of the previous impact of the past inputs vanishes. So this is forgetting of the past inputs. And the total norm of the hidden state converges to a constant. Now, Glarot initialization is exactly the only possible choice in the middle of these 2 cases, where the contributions of past inputs are stable, and the norm of the hidden state grows linearly with the time t. So we see that the norm here still grows in the sequence model, but it grows somehow benignly, not exponentially, in the sequence length t. Now, the big question. So is this Glarot initialization that is stable for feed-forward networks actually stable for long-range linear recurrent networks? We saw that from the point of view of infinite width theory, the answer should be yes. But if you look at modern papers on recurrent models, they do use Glarot as a baseline, but they always need to add an extra rescaling on top of this Glarot initialization to ensure stability. Because vanilla Glarot actually usually explodes in practice. But somehow there has never been an explanation in the literature why it explodes. And now I want to tell you that there is a nice way to see, like nice intuitive way to see why Glarot actually should explode, also theoretically. So remember our linear recurrent network with the hidden state HT, and let's just write it as in its unrolled form, which depends on the moments of our weight matrix W, right? So we see that the whole signal propagation just is controlled by matrix moments in linear models. So to see how this hidden state behaves, we may look at the spectrum of the matrix W. And the theorem on the slide, it basically characterizes the spectral radius, or the largest eigenvalue of the Glorot initialized matrix W. What the theorem says is also summarized on the right-hand side on the figure. So basically in the infinite width limit, if we look at the Glorot initialized matrix, the whole spectrum of the matrix lies within the unit circle on the complex plane. These are non-Hermitian matrices, by the way, so the eigenvalues are always complex. And at infinite widths, we have the famous circular law, which says that the spectral radius is just 1. But now a maybe less well-known fact is that at finite widths of finite matrix size n, there is a small correction to the circular law that makes the largest eigenvalue of W a bit larger than 1. And roughly the size of this finite width correction is of order of 1 divided by square root of n. The theorem here, it gives also the exact expression for this correction. And on top of this, it tells us that the distribution of the spectral radius is Gumbel. And this is true for both complex and real matrices. Okay, so looking at this theorem, we can immediately see that it already suggests instability in the hidden states as long as the sequence length t reaches the square root of the width n. Because when we multiply such eigenvalues a little bit larger than 1 over many recurrent steps of the network, this finite width correction accumulates, right? So that's, I think, already a good intuition, but now let me maybe make it more precise how this spectral effect leads to exploding signals under Glorot initialization. So we have this lemma here that tells us how effects of past inputs explode in linear recurrent networks in the joint scaling limit of the widths n and sequence length t, where the scaling is such that t grows proportionally to the square root of n. And the result tells us that suppose we have our Glorot matrix W, we take its t moment, multiply it by some input u, and then the properly rescaled norm squared grows at least exponentially in our alpha squared, which is the ratio between the sequence length and the square root of width. And the proof here, like knowing the spectral intuition which I just told you, proof is pretty easy. Basically, this squared norm is controlled by the mean squared singular value of the matrix moment Wt. But the mean squared singular value is just lower bounded by the mean squared eigenvalue. And as we just saw, the mean squared eigenvalue for large sequence length t will be just dominated by largest eigenvalues, which are larger than 1 by something of order of 1 divided by square root of n. Yeah, so of course, I don't write everything here. In the paper that I cite, we also figure out the exact expression using some random matrix theory, but the logic is just this. And from this lemma, we can immediately figure out how the actual hidden state in linear recurrent models behaves. So if we look at our rescaled norm of the hidden state, it will also grow exponentially in this term t squared divided by n in the joint scaling limit. And this already tells us that Glorot explodes, right? So let's look again carefully at this result that I just showed you, that Glorot explodes. So here, just reminding that we are considering the joint scaling limit, where the widths n and the sequence length t grow together with a given scaling. And this, as you can see in the figure, gives us exponential growth in the hidden state norm for large enough sequence lengths. But remember that in the infinite width limit, from the analogy with feed-forward networks, the norm of the hidden state may only grow linearly with the sequence length t. So we see that the pictures here, they compare results of the classical infinite width analysis that you will find throughout the literature and our joint scaling analysis on these long-range recurrent models. What we see is that the joint scaling analysis reveals instability of Glorot initialization that's completely hidden by the infinite width analysis. And also, maybe even more interestingly, this analysis shows us the difference between recurrent and feed-forward signal propagation that we couldn't see at infinite width. Okay. And based on this theoretical understanding of why Glorot actually explodes in practice, we can also directly come up with a principled way to rescale Glorot initialization to ensure that it doesn't explode. So you remember that the spectral radius, according to our theorem from the beginning, is a Gumbel variable. So we can just rescale our Glorot initialization based on Gumbel quantiles. Suppose AP is a P quantile of the Gumbel distribution, and then it gives us a rough upper bound on the spectral radius using this quantile for large weight matrices. Then we can just use this upper bound to rescale our vanilla Glorot initialization. And this ensures that the spectral radius stays below 1 with a certain probability and allows us to mitigate exploding behavior with this probability. So the argument is that this kind of rescaling replaces the ad hoc rescaling used in the literature so far. Okay, so now up to this point, I only gave you this spectral intuition, which was nice and simple. I think it's pretty easy to understand it, but it could only give us a crude lower bound on the growth of the signal in recurrent networks. So now I want to tell you about newer results that are much more precise in the sense that they give us exact finite width behavior of signal propagation in linear recurrent networks. Okay, so it's a complicated theorem. Basically, what we have here is that we define two signal energies just for notation. This energy S and T is just our finite width norm of the hidden state divided by M. And Q and K, it's the impact of an input U after K recurrent steps, right? So the theorem on the slide tells us that for complex Gaussian for complex Glorot initialization under fairly general input sequences, we only require, for simplicity, that they are whitened, which is also not necessary here. But basically, the input sequences don't have to have any independence across time. It's a pretty general result. So we have that we can figure out the exact closed formed expressions for both signal energies S and Q for any finite N, T, and K. Okay, and the expressions are in the theorem. They are a little bit complicated. Here in the Q, for example, we have the difference of the rising factorial and the falling factorial. And these expressions look like that because they come from combinatoric reasoning here. So maybe it's hard to understand from this theorem how they behave. So maybe let's better look at the pictures. So here you see how the energy S and also the energy Q behaves depending on how we scale the sequence lengths together with the network's width N. And in both pictures, I separate the behavior of these energies into three different regimes. The first one I call the subcritical regime. Here, the sequence length grows slower than the square root of N. In this regime, throughout this regime, infinite width predictions actually hold. And in particular, Glorot initialization should be stable in the same sense as in feed-forward networks. Like you see here in this regime, our energy S and T grows linearly with T, as should be at infinite widths. Now, exactly at the critical regime where sequence length scales the square root of width, finite width deviations become order 1. So here the behavior becomes qualitatively different from the infinite width predictions. And finally, here there's also a supercritical regime where the sequence length grows faster than square root of n. In this regime, the finite width effects dominate, and in particular, we would have rapidly exploding signals in something like Gilroth initialization. So somehow together, these results now give a precise answer to the title question of this talk. If the question is how long does infinite width last? We see that here it lasts exactly until the sequence length reaches the order of square root of n. In the paper, we also give expressions for how the signal energies behave under all these scaling regimes, like how signal energies grow in each of them. But perhaps the most interesting one is the critical regime, because here we have a non-trivial finite limit for signal energies. So the expression for the energy Q here, it involves this hyperbolic sinus, and the expression for the cumulative signal energy S&T, we can get it by integrating our sinus. And this happens at the critical regime where the width T, the sequence length T grows as square root of width n. And this expression is nice because basically it allows us to compare. It gives us a simple formula that we can already use in practice to understand how signal propagation behaves. So here in the figures, you see empirical results for various finite values of the width n and the sequence length t, plotted against the theoretical expressions for the critical limit. And you see that for a broad range of finite networks, this critical limit expression already gives us a good enough approximation of the practice. So we don't necessarily need to compute all the factorials that I showed you before. It's enough to look at much simpler expressions here at the critical limit. Another thing to note is that the results, these sharpest results I showed you so far were for complex weights. But the reasoning in the paper also directly gives us a lower bound for the real weights. Basically, if we imagine an identical model, identical linear recurrent model with real weight matrices, the signals in such model will grow only faster than in the complex model. And here's also the empirical verification of this statement. What you see here is the empirical signal energies for real recurrent models plotted against the critical limit or the complex case. So indeed, the real case explodes faster than the complex case. Okay, now at the end, maybe I would like to give you just a very rough idea of the method we use in the proof here of such results. And I would again focus on the difference between feedforward and recurrent networks to explain why the recurrent case is much more challenging. So in general, to figure out how signal propagation behave, we need to understand how the mean squared singular value behaves. And here in the slide, I just tried this mean squared singular value as a trace of a long matrix product for feedforward networks. And I can also expand the trace using the sum over the indices of the matrices involved in this matrix product. So far, nothing happened. We just replaced this trace with a sum. But maybe one thing to notice is that since we are dealing with the complex case, there is one conjugated entry for every layer of the network. And there is one corresponding non-conjugated entry for every layer. Okay, now we have a big sum of expectations of Gaussian monomials. And as usual, we can apply Wick theorem to this expectation. The Wick theorem lets us rewrite the expectation of a Gaussian monomial as a sum over possible pairings of the Gaussian entries in the big product. And for every pairing, we need to consider the product of the covariances generated by this pairing. Yeah, so maybe you've never seen this. It's a little bit scary, but the idea is actually pretty simple, and this is basically a standard way to convert these linear algebra programs into more like combinatorial problems. Yeah, so for recurrent networks, everything is particularly simple here because actually in this sum that we have in the weak theorem, where we consider all the possible pairs of the Gaussian entries in this long product, the only entry that gives us a non-zero covariance product is the so-called ladder pairing, that for every matrix of a given layer pairs it to the non-conjugated matrix of the same layer. Okay, and this is just because in the feed-forward case, all the matrices are independent between layers. So therefore, this sum just ends up being a single term, and we can calculate the contribution of the single term, and after simplifying everything, we just get that this long trace is equal to 1. Okay, so this is for feed-forward networks. But now let's look at the recurrent case. So in the recurrent case, instead of the product of many independent matrices, we would have a matrix moment WT, right? Now, once again, rewriting it using the matrix indices, gives us a very similar expression, but now our problem is all the matrices are, or all the entries are potentially dependent here. So instead of only caring about a single ladder pairing that was important in the feed-forward case, now we somehow have to account for much more possible pairings. And now the problem moves much more towards understanding what kind of pairings are possible and what is their contribution from the weak theorem point of view. So basically, now in the recurrent case, we need to think of the sum over pairings, where each pairing has a certain contribution based on how many matrix indices it contracts. And I'm not going to explain here how exactly we figured this out. It's in the end, you can see the paper to see the actual method. But the interesting conclusion maybe is that so we have the first order 1 contribution from the ladder pairing, but the second non-trivial contribution in the recurrent case has this form of proportional to t squared divided by t to the power of 4 by n squared. So you see that this term doesn't vanish anymore when we have our sequence length t growing as the square root of the width n, right? And maybe this term can also be interesting from the point of view that the first correction is not of order n, but of the order of 1 divided by n squared right away. Okay, so let me summarize everything that I said so far. So we saw that stability is an important problem in long-range recurrent models, but the theoretical understanding seems to be somehow limited by reliance of the signal propagation theory on the infinite width limit. And in the infinite width limit, where the sequence length is fixed while width tends to infinity, we saw that recurrent and feed-forward models behave the same from the signal propagation point of view. And this means in particular that standard Lorentz initialization is predicted to be stable in long-range linear recurrences. But then we looked at our more refined joint scaling analysis, where we saw that infinite width predictions actually only hold when the sequence lengths are not larger than, are smaller than square root of width n. And as long as our sequence length scales larger, scales faster than this, infinite width predictions generally break. And this means in particular that Lorentz initialization becomes unstable in this case. And we also start seeing the qualitative difference between feed-forward and recurrent models that we didn't see at infinite width. So overall, this highlights that our finite width and joint scaling analysis better captures the realistic performance of long-range recurrent models. And also in general, it shows maybe the benefit of going beyond the infinite width theory in long-range problems. Okay, so that was it. Thank you for your attention, and I would be happy to take questions.
Recording stopped.
Thank you so much for the talk and for explaining the math. Are there any questions from the audience? Maybe I could start with the first one. I have a question. So your proofs, they're all based on this Glorot initialization. Of course, you explained why that is, right? I was wondering, how does it extend, or does it extend basically your result to different initializations? Or how does it
Do you mean the ones
compare?
that are not Gaussian?
Yes,
Or
yes.
yeah, I mean, so
So where is the
I think
limit?
that
Basically, where does it break, right? So does it
yeah,
is my question.
so the proofs break for non-Gaussians, and I think this is a little bit a general problem of the signal propagation theory, that the best results we have in all the literature is, of course, for Gaussian initialization. Can one extend it to... So for recurrent network, for feed-forward networks, there are some signal propagation results under joint scaling that are under more general initialization. But for recurrent models, yeah, I don't really know if there are any results beyond Gaussian initialization. Basically, you saw that even in the simplest linear case, the actual joint scale analysis ends up being mathematically heavy. And somehow we rely a lot on this weak theorem. And as soon as we don't have this, we have to deal with something like cumulants. So maybe one can think of extending it, but I've never seen anything like this.
It looks complicated for Gaussians. So.
Yeah, I mean, I think that so there are sort of standard ways to go beyond Gaussian. So instead of basically weak, we take some generalization of weak, but can one solve it as nicely as here? I'm honestly not sure at this point.
Right. One more question. So you mentioned linear, you're talking all the time about linear recurrences. And if I understand, you do not have non-linearities, right, in between? This is what you mean.
Yes, here we don't have the non-linearities. So part of the motivation is, of course, that it's simpler. And second part is that, well, people indeed use linear models now. Yeah, also extending this to non-linearities is actually something I would say I'm looking at the moment.
Oh, okay. Because I wanted to ask, basically, can you introduce something as simple as ReLU, and how does it change the result? But
So the first problem you get is that ReLU doesn't make sense for complex networks.
Okay.
That's the first problem is like.
So what do you insert? What do you use?
I mean, well, one can cut either the angles of ReLU, or one can take the real part of the ReLU only. That's also a little bit of a question: what's the appropriate activation to choose? Because in the end, real long-range models that exist are something like LSTM, which is way farther from the model we use here. But somehow real models that just have a simple activation and are recurrent and long range just don't exist in the literature. So it's even a little bit hard to understand what to look at.
Thank you. There is one more question. Can you see the chat?
No. Yeah, sure. One moment. Can improve
Do you
currents
think we
used,
can improve the current initialization schemes using modern recurrent models? Example, the initialization of the decay metrics in Mamba. Do you have any intuition? Great question.
Yeah, so I think that the motivation behind this work also was that I looked at these long-range models, and they always use, like Mamba, for example, they use quite complicated initialization and parameterization schemas. And for me, it's very unclear why this is necessary and what it is necessary. So I think what we can improve is maybe at least removing the unnecessary parts, because even from the point of view of the results here, so I went to papers on long-range recurrences. They say, oh yeah, we like find empirically the constant to rescale Glorot initialization to make it stable, and then we insert 10 things on top to make it perform better. But then you just use rescaling that we have from the theory, and it performs almost as good as all of their complicated add-ons, right? So I think that, at least from my point of view, the first step that we can think of here is to use theory to understand what's important, what's not important. in the existing models and yeah, leave only important things. So that's at least my reasoning here.
Thank you. Are there more questions? No, yeah. Thank you on the chat. Are there more questions from the audience? Doesn't seem so. The last chance. Great. Thank you so much for staying with us today and for this wonderful talk and explaining the math. It's much, actually, it's much more clear than reading the paper, I must admit.
Yeah, well, I mean, in the paper, I think it's much, there's also much more.
This is true, yeah. Right. But thank you for all the explanations.
Okay, I was not sure if how much math I should include, but it's nice that it was useful.
Great. Thank you so
Okay.
much.
Then,
Then good, yeah, have a nice evening, everyone. Bye.
okay, then goodbye.
Thank you. Bye.
Bye.
Thank you. Bye. Hey everyone. I'll sort of take the moderation today. So Peter, how's it going?
Hi, how's it going?
Good, good. Okay, so in if Hannes joins, then maybe I can, even if briefly, just record. If not, then we can go ahead and do it. See.
Peter, I think I can't make you host, but mm, can you just record to your own computer? Then you shouldn't need host the stuff.
It just says recording features can't be started until the host has joined.
Oh. Hmm. Wait a second, then maybe I can try. Yeah, otherwise we'll just have no recording for this one. Mm. Okay, yep, I think I don't know how you shouldn't always does it without being a host. She manages to record somehow, but yeah, then maybe we just don't have a recording this time around.
Okay.
The airplane is taking off now. Okay.
Okay,
See
never mind.
you.
Okay, that's good. Yep. All right. So then do you want to start sharing, Peter, and then we can
Yeah,
get going? Yeah.
sounds great. So we're not able to get screen recording for this one.
Yeah, I think so. I mean,
Okay, cool. Right. Yeah, cool. Well, thank you for having me. Really excited today to talk about some of this new work with flux matching. This has been something that I've been working on for quite a while, so it's quite satisfying and also I'm really happy to finally be able to kind of talk about it with you guys. But yeah, to introduce myself, my name's Peter. I'm currently a second year PhD student in the computer science department at Stanford, where I'm co-advised by Xiaojie Cho and also Stefano Erman. And a lot of my research is involving generative modeling methods with its specific applications in biology, specifically single cell biology. So yeah, so the agenda for today's talk is we'll go over some brief background, some like the more philosophical goals, some key terms that we should be familiar with, and then go into flux matching, some of the intuition and formulation, and then finish off with some of the fundamental capabilities that flux matching enables that previous methods are not able to do. Cool. So before I get into I guess the technical details, I want to start off with a more philosophical discussion. So one of the core goals of generative modeling, at least historically these past few years, have been, how do we sample from P data, realistic samples from P data. So this has been, we've seen with diffusion models and flow matching models, current models are quite good at sampling from P data. So um, there's actually, I would argue, a secondary or meta goal of generative modeling that in many domains, like scientific domains, are arguably as important as just sampling from P data. But there's, we have these like kind of these two core objects. We have our generative model that we learned from some data set, but we also have some knowledge that exists in the world, built off of humans. So we have a lot of structures or priors or inductive biases that we know about our system of interest. So one of the key goals is being able to actually impose a lot of this knowledge, so this structure, these priors, these inductive biases, into our generative model. Um, to, for example, improve performance. But likewise, we should also be able to extract new knowledge after we've learned a generative model. So this should be able to, we should be able to extract new knowledge that we can build new structures or priors or inductive biases with. So yeah, we've kind of seen, diffusion models are quite good at being able to sample realistic, images or other, continuous data from P data. And they do this by, effectively, you have your empirical distribution or your empirical data set of, for example, dog images, or another example could be like single cell gene expressions. And diffusion models learn something called the score function, which is this gradient log density. And specifically, diffusion models learn this kind of noise annealed, or many score functions for many noise annealed versions of your data distribution. But the core intuition here is it learns a single vector a score function where if learned perfectly, sampling or moving along this vector field, starting from initial samples, eventually will converge to a stationary distribution, which is our P data. But interestingly enough, there's actually many other alternative vector fields that generate data. So we call these kind of generative vector fields, which loosely speaking is if we sample, we have some stochastic process on top of this vector field, eventually will converge to our stationary distribution. So cool, interesting thing about this is these alternative generative vector fields actually provide an opportunity to, impose or extract some type of structure or prior inductive bias, this knowledge, so to speak. So there's this well-known condition or this classic condition that characterizes these alternative vector fields. And as long as this condition is satisfied, we can kind of, loosely speaking, guarantee that this vector field generates data from your distribution of interest. So yeah, let's look at this component by component, but we start with this, SD down here, this diffusion process where my cursor is, if you can see that, which is basically just saying xt, which is just a single red dot here. The change in the position of this red dot is a result of a small movement along your vector field f theta, plus some Brownian, a little bit of Brownian motion or noise. And as long as this condition, so this condition is satisfied, which is the divergence of the flux of f theta. If the divergence of the flux of f theta is equivalent or equal to the divergence of the flux of the score for all x, we can guarantee that if we simulate a diffusion process on this vector field f theta, we'll eventually sample from our stationary distribution, which is our data distribution. And kind of this, the flux of f, the divergence of the flux of f being equal to the divergence of flux of the score is a little bit of a hint at why we eventually call our method flux matching. And the core thing I want to note here is that infinitely many f or f thetas satisfy this condition here, or satisfy proposition 2.1. So pictorially, we can kind of see on the right-hand side where my cursor is, there's a single point along the space is a vector field. Infinitely many vector fields within this rectangle satisfy prop 2.1, meaning there's many, many vector fields that can generate data. And the score function is just a single member of this family. And these alternative vector fields, with potentially useful or advantageous attributes, we can actually now select while still guaranteeing that it samples from our stationary distribution. So we've seen with diffusion models, the score function is quite easy to learn. There's been a wealth of literature that have given us quite established tools for learning the score function, which is basically just trying to minimize something called the Fisher divergence, which is this term here, which is just kind of the pointwise MSE between our learned vector field f theta and some ground truth score function, weighted by our data density. And we can learn this or minimize this Fisher divergence via something called either the implicit score matching or via denoising score matching, where denoising score matching is generally biased, but as if we just only add very, very little noise, this bias is pretty negligible. But the core challenge with uh, is actually learning these other alternative generative vector fields. We have all these tools to learn the score function, but no tools to actually learn these other potentially useful vector fields. And that's where flux matching comes into play. If there's really one thing to take away from this entire presentation is the goal of flux matching is to be able to learn this family of generative vector fields or these alternative vector fields in a efficient and scalable way.
Before you continue, just if to pause here for a second, like at this point, I can maybe later it becomes clear, like maybe it's sort of like a construction where it's like you start with what you end, like the results that you have, but a priori, like, is there a reason that you like had going into as to why you would want to learn other sort of vector fields than the score?
Yeah, so I think this goes back to the kind of the meta goal of generative modeling. There's different inductive biases or structures or priors we might have about the dynamics of how we generate data. So you can actually imagine, so like at least within single cell biology, right? Like we have gene regulatory networks that could be used to represent, or that could be represented by some type of like ODE or SDE. We can kind of learn some type of, SD that generates, some snapshot of single cell data that then we can use to learn, the relationships between different genes. But there's other examples where we have priors or structure that we have on our vector field, which are not the score. So this flux matching enables you to learn these alternative vector fields that impose these priors, but still guarantee that you sample data. And we'll go through a few examples or applications in the later slides.
Yeah.
So again, let's start with the Fisher divergence. So now I'll get more into the mathematical details of how do we actually learn these alternative vector fields. So we again start with the Fisher divergence, which is just the pointwise difference between f, your learned model, your learned vector valued model, and the score function weighted by your density. And then again, recall our condition that if satisfied, it guarantees that f will loosely generate data from p data. The question now becomes, how do we actually satisfy proposition 2.1, but still operate in a Fisher divergence like geometry, where we're comparing vector fields? So we introduced something called the projected Fisher divergence, which is, intuitively this divergence that does not penalize any p data preserving dynamics, but does penalize any p data violating dynamics. So you can imagine you can add any curl, so you can add any divergence or vector component that, as long as the divergence of p with p data with this vector field is 0, it should be invisible to this projected Fisher divergence. And we do that by essentially defining this projection operator, this big pi flux, which projects F onto only the gradient or mass moving component of F, and then compare that directly with the score function. So you can think about this projection operator as stripping away all the non-distribution moving components and only looking at the gradient distribution moving component and then comparing that with your score function. So this allows you to still satisfy prop 2.1. So as long as that this Fisher divergence is equal to 0, this proposition is satisfied, while also maintaining some type of vector value or this vector field-like geometry. So before we move on to the flux matching loss, which gives us a way to actually estimate this tractably, do we have any questions?
So, just can you describe more what does it mean for F to not have components that move the distribution?
Yeah, so that's a really great question. So if we look at this equation here where my cursor is, um, the main goal of this condition is we want to be able to to learn some F such that the divergence of the flux of F is equal to the divergence of the flux of the score function. But you can actually show that if you just add any additional vector component where this vector field, the divergence of this vector field weighted by the probability distribution is equal to 0, this condition still continues to hold. So
Oh,
this vector field could be any curl or like any interesting dynamic, but it still maintains this equivalency.
sure.
So what this projection operation does is it strips away any of those non-distribution moving components, aka any value where this is not 0, where this divergence of the flux is not 0. Or yeah, is equal to 0. So it strips away
Yeah.
those components. So yeah, let's get into the flux matching loss, which provides a way for us to tractably estimate this projected Fisher divergence, which is obviously quite hard to calculate.
Okay, I
So
have a
there's
question.
Mhm.
So you didn't define like what is pi flux? I don't see the definition of pi
Yeah.
flux.
So yeah, that's a great question. So yeah, I think I decided to take that way because I didn't want to include too much math on a single slide, but you can kind of just imagine that this projection operator is just um, is essentially only looking at F through the lens of any distribution moving component. So if you plug in this equation into, let's say, like this pi F into here, um, it should be equivalent to a gradient component of only the mass moving component.
You see. So
Yeah.
okay. Yep. So just to make sure I understand. So if I define G equal pi flux of F, then G also satisfies the proposition 2.1. Is that correct?
Yeah, exactly. And then this G would be the gradient like a gradient field or the minimum representation of F that satisfies the exact same, yeah, like divergence of the flux.
Okay, makes sense. Thanks.
So yeah, we'll start by defining two objects that are like quite important. First is this U theta term, which is just the difference between our learned model F and the score function. And then we also define R theta, which is this term here. And R theta is also known as the Langevin-Stein operator on U theta, which is just the divergence of U plus the dot of U with the score function. And intuitively, you can think of R theta as this scalar value that measures how much or how far away F theta is from being a data generating vector field, um, while being also blind to any distribution preserving component. So there's really four main steps of how we connect this intractable projected Fisher divergence to a more tractable flux matching loss. If this is interesting, we could get to it later, but I think for the sake of just, I don't think it's super important what the technical details are, but the main intuition we want to gain here is we have our intractable projected Fisher divergence. We take a series of steps to get us to a tractable flux matching loss. And in the coming slides, I'll give a bit more geometric interpretation of what is going on here. So yeah, let's show how this flux matching loss is calculated in practice with just a simple example. So we have a mixture of three Gaussians. So this is our P data. And then we sample some mini batch of samples given by x0. So because back here we needed access to the ground truth score function, we don't have that in practice. So we approximate that with a mini batch version of it, which is asymptotically unbiased as we increase the batch size to a very large number, but it is biased in the finite samples. But we kind of see actually empirically it doesn't really make that big of a difference. So we construct this approximation of the score function. We then calculate this U theta term that we talked about, which is the difference between our model called on x0 and the approximated score function. And this is where I think I'll explain a bit of the intuition on why we're doing this. We then do MCMC. So we first sample some simulation horizon T, and then do Markov chain Monte Carlo to this horizon, typically using unadjusted Langevin dynamics to get to xt. And we do this unadjusted Langevin dynamics with our approximated score. We then get our xt values, which is our simulated out samples. And then we calculate this, where my cursor is, this Langevin-Stein operator. Which again, this Langevin-Stein operator measures is a scalar measurement of how far f theta is from a distribution generating vector field. So I'll explain some intuition on why we're doing this MCMC process. The main thing to note when we go back to our original construction is this R theta value is actually quite important. We could directly just say like we could directly use our theta as a way to measure the difference between how far f is from a data generating vector field, while also being blind to any data preserving dynamic. But the issue is because we take the divergence of this probability flux, we actually operate one derivative below the vector values that we actually care about, which again goes back to our projected Fisher divergence. We want some type of projected or Fisher divergence like geometry while still being blind to these distribution preserving components. So R gives us this distribution preserving blindness to distribution preserving components, but it operates one derivative below where we actually care about, which is the vector fields. So this MCMC process almost loosely inverts this derivative to go back up into the vector field level. So then we collect the necessary terms, so U theta on x0, and then this gradient of R on xt, and then we backprop on this term here where my cursor is. So I think the core takeaway to get from this geometric this geometric example is we get initial samples, we MCMC out, and then we calculate some terms, which we then collect to define our loss.
Wait, and and so can you go back 1 second to the slide before?
Yep.
So okay, so U is F, U is okay. I'm trying to think when you're backpropagating into it's a loss on U.
Yep.
Okay. Yeah, okay. Can you go forward? I see. So the loss term here, I see, is in the U term.
Yep. So yeah, we actually show that this if we just go back to the math, I think I guess if this crowd is interested, we can talk
Yeah.
about it. So we make really, I'll actually go through it step by step. So we start by making this equivalence between the projected Fisher divergence, which is intractable, into this essentially infinite integral of autocorrelation for R's. So we calculate R at x0, then do some type of MCMC out to xt. So this xt condition on x0 just represents a simulation chain from x0 to xt. Calculate R again on xt. So these are equivalent. We then do integration by parts. And the reason we do this is why we see this u and this gradient R term is because of this step here. And this step is we actually found to be quite necessary because to calculate this divergence term, where my cursor is intractable in high dimensions. So we approximate it with like a single sample Hutchinson's trace estimator, which is quite noisy. And especially when you dot it, like when you multiply it with another uh, you know approximation, the noise kind of blows up. So or the variance kind of blows up. So this essentially allows us to do this like essentially a variance reduction. Um, and then after this, we show that in terms of the gradients, line 2 and line 3 are equivalent in terms of the gradients with respect to f theta, up to a factor of 2. And that's how we arrive at this final loss. We just Monte Carlo this, integration with, and then we get this ultimate line for flex matching loss.
And where does this, is that subgradient, right? G?
Yeah, it's a stop gradient. Yeah.
Yeah. So
Meaning
where
that
does
we
that
don't
come
back apply
from?
a stop gradient. Yeah.
Yeah. So where does that come from? Like, what's the step that?
Yeah. So step 2 and step 3, like that's one of the main algebraic manipulations is we can actually show that step 2 and step 3 are equivalent in terms of the gradients up to a factor of 2, which is quite nice because now we can actually reduce having to backprop through this really expensive term.
I see. Okay.
Yeah, and if you're interested in how we kind of show this, it's in the appendix, in the proofs of the appendix of the paper. Great question.
And it's just one thing is probably I'm just like missing here is why does the integral go to infinity here? Is t goes to infinity?
Yeah, so there exactly. So there's a well-known in some like stochastic process textbook, they were able to show this equivalency between essentially some version of this projected Fisher divergence with this like infinite integral over autocorrelations.
Okay.
But yeah, you can essentially go back to this intuition, right? The intuition is R theta is essentially doing this projection, but one derivative below, because R is a scalar value while we're trying to work at the vector valued geometry. This infinite integral essentially uh, moves x0 to xt. So we're able to essentially invert this divergence operator to get back to the vector value function um, that is still blind to any distribution preserving dynamic.
And yeah, and part of the reason you have to do all these samplings is like you're trying to get at all the different potential f's whose projection would be like would have a divergence of 0 for this flux.
Exactly.
I see.
Yeah, exactly.
Okay.
Any other questions before we move on?
Because I have a curiosity. So
Mhm.
I look at the first equation and you go back to the first equation. I is that the ergodicity? Like the I think is that its code? well, I'm not sure if it's ergodicity, but it's a kind of like this. If you have a stationary distribution and you sample from it, it equivalent to you just do integration for like infinite time. I think it's called ergodicity.
Um,
Maybe it's different here.
I think that I see your point, but I think the precise definition like of ergodicity is like, isn't it like, um, I guess actually it could that could be true. I'm sure that there's some connection. But yeah, again, it's like you're trying to estimate some like term by using I guess yeah simulations or using MCMC. But yeah, I think th there must be some connection here. Yeah.
So just one last question. So in the definition of function R, you have the term p to the power like p to the power of minus one, and that term is well I so the purpose is to get the diversion of p times u equals 0. Then you need the denominator. Yeah, you need the denominator, the inverse of p in order for deriving the first equation, right? Oh, like
Um,
so I just want to get the intuition of get the inverse of p into the definition of R.
yeah. So actually, the 1 over p data cancels out because when you expand just the divergence of the flux, you get this additional p data term that will cancel out with this inverse of the p data, which is why you have why we get this term here.
Um,
Yeah, because otherwise, yeah, having this inverse of p data would be quite difficult to work with. But yeah, we are able to it comes out to become this equation here. So all
I
we
see.
need is the data score and then the youth data.
Yeah. Is the question about like what R theta evaluates to, or is it about where the inverse comes from?
Yes, this question is where is the inverse come from? Yes, but he
Okay.
Oh,
answered.
right. Yeah. Okay. So where the inverse comes from, it's actually more of a convenience because ultimately we don't care about this like we only care about this divergence of the probability flux.
Yes.
Um, but the minimizer of this divergence of the probability flux is actually equivalent, like the minimizers of with respect to theta is actually equivalent if we have this inverse of p data or this weighting by the inverse of p data. And we add this for convenience in order to get something that's a bit more tractable here.
I see. Yes,
Yeah.
that's nice. Yeah,
And
thanks.
this connects to, I think, a lot of like R has this rich history of like being known as the Langevin-Stein operator, where there's a lot of tools of looking at, this R theta term.
Yes, okay, so you have your samples, right? Just to go, this just to summarize the sort of algorithm so far. You have these samples, you roll out some MCMC with your score to get your uh yeah your XTs. You compute sort of your U and R theta over that, and then you compute a loss, which you can sort of backpropagate.
Precisely, exactly.
Yeah.
Yep. So yeah, with this loss, we can now essentially learn any point or any vector field within this rectangular box, which represents all the vector fields that can loosely generate data. And
But you don't
again,
know which one, right? You've
exactly, you have
learned
no
at the
constraints right now, right?
yeah.
So you can essentially with Flux, it's a essentially a unconstrained like it's an underdetermined problem. There's many vector fields that satisfy prop 2.1, and Flux
Yeah.
matching right now treats any value or any point within this as a minimizer of the Flux matching loss.
And And is that a problem in the sense that you're learning many vector field? Like, how do you have consistency across when you're generating a data that you're using a vector field that's sort of consistent across the different time points if you're doing it like iteratively?
Um, So that's where we'll talk in the coming slides on how do you enforce specific structure or constraints on your vector field. Because I think the entire point is like you actually don't it doesn't really make much sense of just having unconstrained vector field because then you can learn any vector field. It's more if you have some prior or some uh, specific advantageous like characteristic you want about your vector field that then you can enforce within this, this vector field while still guaranteeing you sample data. Um, but yeah, like it's a good question. So if you have like a iterative process, how do you guarantee that this um I guess is
I
your
guess
question like
yeah.
is your
Because
question
my
like
question
how do you
is,
guarantee that this vector
if you
field
have like
satisfies?
x, right, like at the point of where you've learned your function f, but f could be anything, right? It could be just a score, or it could be something else. So like, how do you know what it is at the point of inference? And is it one? Do you learn just one vector field, or have you learned all of them?
Right. So again, this is like an ill-posed problem. Like there's many vector fields that satisfy the flux matching law. So essentially your model could be learning any point, and you don't really
Yeah.
know unless you add constraints. So yeah,
And I
like
guess,
yeah, we don't really know what the vector field would be. Yeah.
yeah.
Unless you
And
enforce
is it a different training you would converge to different solutions and different vector fields?
yeah. Yeah, like yeah, if you assume like there's like noise within your optimization and like there's
Yeah.
also I guess your model itself always carries some inductive bias about the Fs or the vector fields that you should learn. So like if you have like a UNet or some other like transformer architecture, each of them kind of carry their own set of inductive biases that kind of constrain the space a bit. So you're not always operating exactly like completely unconstrained unless your model F is like fully expressive and can represent all possible functions.
Is there a reason to not think that you would like for some reason always degenerate to just the score?
Um, I guess why would that be? Like in the case that
Yeah,
if
no,
any of
there's no
these,
like constraint on it. I'm just saying,
yeah,
is it like for some reason like the simpler solution?
yeah. So there's different interpretations, right? The score is actually just the L2 norm minimal, like the p-weighted L2 norm minimal vector field. So if you have some constraint on your vector field being like, I want the shortest or like the least
Yeah.
uh, L2 magnitude of the vector fields, you would eventually get the score function. Um, but like what the simplest vector field is to a neural network is really based off of how you parameterize the neural network. Um, yeah.
Okay.
So yeah, I think this kind of goes back to some of the questions I've been asked. Now that you can learn the family, how do you really choose the right one or the beneficial one, right? And it really depends on your application. This goes back to, this meta goal of generative modeling of, how do we impose or, extract different priors or inductive biases on your generative model. So this is really the core challenge or the core effort that a practitioner has to think about when they use flux matching. You have some inductive bias or you have some prior. How do we actually enforce this or impose this within our vector field? So I'll kind of give you two generic recipes to do so. The first one is you just add some application specific loss. So you have like your main flux matching loss that when minimized guarantees your vector will generate data. But then you have also some application specific regularizer. So for example, if I want like a sparser vector field, I could add like a L1 like sparse regularizer to the flux matching loss. Um, but a second option is also you can just directly enforce some constraint on the parameterization of your neural network. So for example, if I have a known structure between or directed structure between variables in my data, I could, if I'm learning a transformer architecture where there's a tension, we can mask out the tension in the specific way that we have priors on. So that's like also another way to enforce constraints on your vector field.
Yep.
And now, yeah, there's one extension to flux matching which is the noise and yield setting. And this is what what diffusion models operate in is rather than just learning a single score function, diffusion models learn a series or a continuum of vector fields of increasingly noise distributions. And likewise, you can do the same thing with flux matching. You just learn flux matching at each of these progressively noise distributions, and you do some type of like weighted sum of the losses at these different noised versions of the data distribution. So now that you have a train model using flux matching, how do you sample data from it? The cool part is actually you can basically use any off-the-shelf, Langevin or diffusion sampler. Like the typical samplers you use for diffusion models or flow matching models, you can actually use with flux matching as well. So for example, right, if we only learned a single vector field at the data distribution or near the data distribution, we can use unadjusted Langevin dynamics to sample from our vector field or our F theta, where we just replace F theta or we replace the score function in Langevin dynamics with our learned F theta. And then in the case of like noise annealed flux matching, where there's a continuum of noise distributions, we can use a lot of the standard like reverse diffusion SDs or probability flow ODEs to sample data. And also interestingly, we can do likelihood calculation in exactly the same way as diffusion and flow models do it, via the instantaneous change of variables. So yeah, it's quite neat because we're able to fit flux matching, like a lot of sampling techniques used for diffusion models naturally fit into sampling for flux matching models. So now let's talk about some of the capabilities or things that flux matching enables that previously was impossible with score matching. And I'll show some of the experiments for each of these capabilities. So the first one is this toy experiment where we have, this mixture of three Gaussians. And the main goal or the main takeaway that we want to show with this experiment is flux matching enables direct controllability over interesting vector field attributes. So at least for this experiment, we're looking at mixing, and we're also looking at this kind of like fun triangle shape attribute, and also the attribute of having a Jacobian that's anti-symmetric. So then if we pay attention to the bottom row, the x-axes is the magnitude of these vector field attributes. So we have like mixing speed, triangle shape, and Jacobian skewness. And the black star is where the score function sits. And then yeah, the y-axis is the standard or the loss under either score matching or under flux matching. And we see that, as we increase the magnitude of these different vector field attributes, clearly, this isn't we won't be at the score function anymore. So the score matching would have an increased loss as we drift further and further away from the score function. But because we, at least within this experiment, we directly enforce that these vector field attributes preserve the distribution, these additional vector field attributes, even as we increase the magnitude, is invisible in the eyes of flux matching. So the loss for flux matching is zero.
And how do you implement the sort of the attributes themselves?
Yeah, so that's a great question. So there's certain things that we can analytically calculate because of this. This is just like a mixture of three Gaussians. You can analytically calculate mixing speed in this very simple example. We define the triangle as just like how much like the vector fields align with a predefined triangle shape.
Okay.
And the Jacobian skewness is just the like how anti-symmetric the Jacobian is. So these are all things that you can kind of calculate by having like a discretization of the domain of your 2D data set or your 2D mixture of Gaussians.
And
But yeah, so
you add the application specific loss for each of them. Like
uh, no, so this is directly so to kind of um to control for all the potential optimization issues and things like that, we just directly enforce we assign a vector field with a like a mixing speed of some predefined value. And then we calculate the flux matching loss along a discretization of this vector field. So we're not actually doing any optimization here. We're just looking at what is the flux matching loss at different points along this vector field with a predefined attribute on this vector field.
yeah, thanks.
Yeah. So yeah, another thing to note is as we increase, so these things that preserve the distribution have a zero loss for flux matching. But then if we actually increase, or if we introduce dynamics or components that actually violate the distribution, then for both score matching and flux matching, the loss increases, meaning that the flux matching loss would penalize these distribution violating components. So yeah, a second capability of flux matching is we can actually use flux matching to fit these mechanistic or semi-mechanistic models. So here we're looking at the application of RNA velocity. So I won't get into the details of things, but the goal of RNA velocity is given a snapshot or like a population snapshot of single cells. I want to learn how I want to learn the velocity of how these cells are moving through time in terms of their gene expression profiles. So there's this paper SCVelo, given by the Fabian Theis's group that learned this mechanistic ODE where you want to learn parameters alpha, beta, and gamma. And you want to fit this ODE to your observed population of cells. So for flux matching, you can actually replace. So in SCVelo, they optimize this or they learn these parameters alpha, beta, and gamma using some type of EM algorithm. But you can actually replace their optimization with just direct gradient descent on flux matching while keeping the exact same biological or mechanistic ODE. So we show that with the exact same biological parameterization and purely just changing the optimization or like what you're optimizing for, you can have much better results over 5 different real single cell data sets. So here on CBC, we look at CBC, which is the cross boundary correctness, which basically just tells you how well does your learned velocity align with expert annotated cell transitions. And consistency measures how smooth or well-aligned vector fields the vectors are with each other. And across these 5 different data sets, flux matching nearly increases or improves performance on all the metrics. Yeah, so
can you just describe the task a little bit? So here, what's the data distribute? Like, what are you sampling?
yeah, so here you're sampling single cell spliced and unspliced RNA.
So, or is it RNA like expression or?
Yeah, exactly. Expression. Yeah,
Okay.
RNA-seq. Yep.
Okay, so
So
you have a like a data of RNA expression of cells in different states, and you learn to sample from them, and then in addition to that, you impose as a structure, like a would this like ODEs or how does it work?
exactly. So you learn this kind of this ODE that is predefined, and you fit alpha, beta, and gamma to this population of cells. And the goal is to be able to say like, oh, I want this to still explain my snapshot or distribution of cells in terms of RNA expression, while still abiding by this mechanistic ODE.
I see.
Yeah. Yeah, we can also use flux matching as a standalone generative learning objective as well. So here we just applied flux matching to 2 different data sets or image data sets, CFAR10 and SLEB-A. And we show that flux matching performs pretty well on these data sets for FID. So there's some things to note. Flux is not at the level of DSM yet, and it's um, could be partially attributed to DSM going through a lot of different engineering cycles over the past few years that have driven down this FID value. But yeah, I think the main point to see is Flux does perform quite well as just a standalone learning objective. But we also see that Flux is a bit slower and takes up more memory than DSM does. DSM again is denoising score matching. So at least for CF, yeah.
No, yeah, I could continue.
So we see with at least the training speed per iteration, Flux is typically 2 to 4 times slower, or I guess 2 to 3 times slower. And then the memory, Flux takes about 2 to 4 times more memory than DSM. But I think the important thing to note here is Flux is not trying to replace DSM. If your entire goal is purely I want to generate data, I want to do it fast, then you should stick to DSM. Flux matching is only useful if you have some prior or some inductive bias you want to incorporate into your vector field. And that's what flux matching enables you to do. But yeah, if you have no prior, you have no inductive bias, you just have samples and want to fit a vector field to these samples, stick to DSM. So yeah, I'll show you a few of attributes that we can optimize for with flux matching that are quite beneficial. So one is this notion of fast mixing generative fields. Loosely speaking, so we can actually learn vector fields using flux matching that try to optimize for the mixing speed. And kind of loosely speaking, a faster mixing field, hand wavy kind of enables you to take fewer sampling steps. So we're able to have accelerated sampling with faster mixing fields. And we show here on CFAR 10 and SLAB A again, where the x-axis is the number of sampling steps and the y-axis is the FID. The fast mixing version of Flux is able to decrease FID with a lot fewer sampling steps compared to the vanilla version of Flux, which is just unconstrained flux matching, and also compared to DSM. And we see the same thing with SLAB A, except the difference between the vanilla version and the fast mixing version is not as dramatic. But interestingly, we found that even just the vanilla version of Flux with no constraints is able to mix faster or have, we can use fewer sampling steps to achieve better performance. And this partially, hypothesizing here that it could be attributed to the fact that the score function or longitudinal dynamics is a reversible process, and reversible processes are known to mix slowly, while flux matching has no such constraint. So it can learn any vector field, and these vector fields could be non-reversible, so they mix faster. And then the last experiment that we have is showing that flux matching enables us to embed structure or directed relationships between variables in our data into our generation process. So here, this is not loading, but so yeah, we had this like spring simulation experiment where we have two coupled springs and we simulate out their trajectories or their positions through time. And we essentially generate a bunch of different trajectories and then learn a generative model over these trajectories. So we actually have some prior knowledge on this. We know that the current position at some time point of these two blocks is only dependent on previous time points. So we can actually incorporate this autoregressive causality into our generation process by, if we train like a attention network here, we can mask out the attention mechanism to make it autoregressive. So the positions at each point can only look at previous time points. So here we train DSM and flux matching with and without this causal mask. And we show, at least with DSM, this causal mask actually hurts performance. So with this causal mask, DSM increases its Wasserstein distance compared to its non-causal version. And this makes sense because the score function, by definition, is has a symmetric Jacobian, meaning that if we have any type of anti-symmetric mask, such as an autoregressive mask, this model then cannot, by definition, learn the score function, which is why it's not surprising to see that this causal mask is hurting the performance of these score matching models. But then, because flux matching has no such condition, we can actually enforce this causal mask on the model, and it helps performance because we're including this inductive bias or this autoregressive causality and time inductive bias. So I think the main point to take away here is we're able to enforce structure within our generation process or inductive biases. So for example, autoregressive causality between variables or between time points, while doing simultaneous parallel generation, which is one of the great parts about diffusion models. We're able to generate all dimensions or all variables simultaneously. So I think that's actually one of the cool parts about flux matching. Flux matching, we can incorporate structure or directed dependencies between variables while doing simultaneous generation. So future works, for example, like video generation, you can do parallel generation of all the different frames in the videos while still enforcing autoregressive in time or autoregressive causality between frames. Some current frame can only look at previous frames. You can enforce that directly into your model.
And what about like we thought about like the cases sort of similar to the cells, but more generally, if you have you're trying to sample like data where there is like people used to do this with like bridges where you just how you go from one, so you have multiple sort of states you're trying to go through, or like you think of like protein, I know this stuff from the work here. It's like the protein conformations. Maybe you have different states that you're going through to go from one conformation to another, and you want to enforce that you pass through these intermediate steps.
Yeah. So at least within this paper, we focus on just a single distribution, but the multi-distribution, like the multi-marginal, like kind of flowing, or you have a distribution flow rather than just a single distribution. That's an interesting problem as well. We partially addressed this within one of the appendix, but like we didn't really focus much on it. But I think this would be an excellent future direction of how do we do flux matching. So again, with a lot of these like kind of distributional flow models or like these diffusion bridges, you only enforce constraints you enforce sample level constraints. So you want this you define some prior bridge between the two distributions, and you want your sample to flow through this predefined interpolant. But we can actually show through flux you can add any type of curl while still preserving the same flow of marginal distributions, but with dramatically different individual particle level trajectories. So that's actually another degree of freedom that flux matching could potentially enable. We just really haven't looked much at the distribution flow setting, but would be really cool as like a future work though.
Nice. Um, any questions from people in the Zoom?
Well, if we have time, I would love to get a little bit more detail about how you control the toy example, like do controllability in the toy example. If we have
Yeah,
time.
sure. I guess do we have a time limit for like when this meeting's supposed to end? Is it at 10?
I mean, not hard limit, I don't think.
Okay. Do you mind if let me go through the takeaways and like the final slides, and then we can
Sure.
skip back to the like your question. So the main takeaways I'm hoping to provide with this presentation is score matching learns a single vector field, a single static target, while flux matching learns this infinite family of vector fields. And the great part about having this family of vector fields is now we can pick and choose vector fields that are advantageous for our application. So vector fields are now a design choice rather than some static or fixed target like the score function.
Apple's dubbed up. Watching it live.
And with our users. And it delivers the same beautiful refractions.
So this time Apple has completely focused on designing Siri from scratch. Hmm. And the features for the kids that are impressive too. So every app will kind of have them. And for the platform State of the Union and others, we will get to see those details. We'll have to where is the dev apple.dev. This is the developer.apple.com, and here we have had the keynote. Next up is platform State of the Union. So I'll stream this tomorrow. And this time it was on YouTube at 4K. And the site had the, since I have an old PC, so on Windows it rendered at 1080p. So I had to switch midway to find a 4K stream. Let me make a tweet, the X post, and then I will call it a day and go to sleep. This looks good. Indentation, the fonts, and the summary. Let me also try to paste in the link to the image playground and photo editing features are quite good. Like it is from the it is not state of the art in any way, as like they have existed in different forms of uh, research previously. It's just that it is refined in a way that is much more extensible, and as Apple does it with their products, accessible to accessible to the mass market. So that's what they bring to the table right now. The developer tools are quite good. The core AI frameworks, the gist that we got right now. And the developer betas are available today, so anyone can dive in. Let's make these headings bold. Should have inserted context related emojis in here, but I don't think so. I have the API to do that right now. I haven't installed that particular extension. Let me draft assistant. Maybe this will work. Oh, it worked. It finally worked. And they have replaced the whole thing too. So I'm deleting the dashes since these emojis look good. Maybe this up, this guy, this. just too different from the thing that we had here. Many of the details that I wanted is gone in the new text that Perplexity formed. So I am specifying prompting it to not change the text. This looks good. All the details that I wanted is here. Let's paste in the built-in public. Let's again go on to the replies. Let's go through the emails. I think I've got many. And we'll be streaming from tomorrow morning then next. Config, log prompts, work, GLN, gamma 4, model pass gate models, PFC AI gateway, integrate deep EPv2, Gemini, KV cache, Wimbledon, fallback, Supermicro, TPP, and Apple. Welcome. This is new. Pocket post. Now talks is Tuesday. This is tips V2. So this is the models of the image text encoder family from Google DeepMind that I am inviting to present in my Cohere Labs computer vision community. Let's see if they have the time to come in and present. Okay then. I think I will call it a day. Let's go to the top exposed here. Vision CD. Yeah, I've applied for the auto scientist. Let's see if I get access to it. China's unitary will dominate global robotics. Yeah, I see it too. The vision is there. Unity is tripling its YOY revenues on 60% gross margins product lines, planning about $300 million of AI R&D spends. This is the robot GIETU Advanced 29 degree of freedom. Approximately $9,000. See the torso, the legs, the head, the arms, the waist. The components that they have had. Good article detailing mostly everything from the Unity's perspective. Reef stack. Okay, I think so. I will call it a day and reconvene tomorrow. Thanks for all the inputs. I hope this was fun today. Bye. Take care. Ciao.